Hello, my name is Aditya Harsh, and I'll be presenting the x16 ISA for CSCI E-93. The x16 is a 16-bit architecture inspired by x86 and MIPS. It features a 16-register array, 16 native instructions, byte and word addressable memory, as well as special features which include a hardware multiplier and barrel shifter. Next, I'll go over the register array. R0 to R7 are 8 general-purpose registers. RS and RT are temporary registers that by convention don't need to be preserved across instructions. Most macro instructions will modify them. %0 and %1 are initialized to 0 and 1 respectively. However, the programmer is free to modify them. The PC register holds the next instruction and can be modified to achieve non-sequential execution. The FP register allows programs to have a stable stack offset. The SP points to the top of the stack in decrements. The return pointer holds the return address to jump back to after a subroutine call. X16 has two instruction types: R-type register instructions with 13 different instructions, and I-type immediate instructions with 3 different instructions. Note that X16 does not support any J-type or jump instructions. Here's the layout for instruction types. R-type instructions have 4 bits for each parameter, and I-type instructions have 4 bits for op and RD, or destination register, but 8 bits for the immediate value. Jumping to a different instruction is achieved by modifying the PC register. A conditional jump can be performed by using a cmove instruction with PC as a destination. PC can be set to any 16-bit value representing a word. In practice, from 0x0 to 0x7FFF. Here are the 16 native instructions. They range from operations such as shifting, ANDing, ORing, XORing, addition, multiplication, conditional moves, loading and storing memory, and moving high 8 bits, moving low 8 bits, or adding 8 bits. There are 30 macro instructions that help improve the debugging workflow, ranging from moving immediates to pushing and popping from the stack, as well as calling and returning from routines and conditional jumps. There are 16 ALU instructions which map 1-to-1 with the 16 native instructions, including the opcode values. The assembler is programmed using C++23. It features address labels as well as various directives such as equal, ASCII, ASCII-Z, space, and byte. The assembler spits out a MIF file and optionally a listing file. There's lots of syntactic triggers such as name parameters and error reporting to improve the development workflow. Here's an example of the assembly code. It's very similar to MIPS, but there's also differences. So for improving readability, what I did was I added support for optional label for arguments, which don't have any functional use, but they're just there to help the programmer better understand what's going on. So if you look at draw that demo frame, for example, I call output string new line as my routine address, but before that I set R0 as string title. So that's one way to help improve the development workflow. And you can also generate a listing file. So on the right side, this is the listing file that gets generated by the assembler, and it contains information such as functions as well as the instructions as well as the macro names. It also has all the strings and data at the very bottom, and it labels the characters because they're all byte packed. The emulator is programmed using C++23. It supports running programs directly, terminal I/O, and stepping through instructions. You can use a generated listing file to help map native instructions to macro instructions when debugging. Here's a demo of the emulator. The emulator lets you step through instructions one by one, as well as just running the program directly without doing any step debugging. So if you hold on enter, you can step through each instruction, and towards the bottom you can see the register values, as well as whenever a register gets updated, it shows you what is the previous value and then what it got changed to. And if you press continue, it'll just start running the program as is, and you can see it work. This project is built with the Altera GE2115. It is able to run programs at full clock speed, as well as having various debug options such as setting clock divide, clock hold, and memory suspend from the switches. You can display contents of registers based on switches, display the FSM state, show various signals from the memory controller, and reset the program using a push button. Here's a demo program running live on the DE2115 hardware. These first 4 switches here can be used to set the register that's displayed. So, for example, by turning on these 4, I show register F, which is equal to 38D. The contents of register D is FF00, so on and so forth. The rest of the switches can be used to set the clock divide. So as I enable each switch, the clock divide increases, making the program run slower. This switch here will set the clock hold, and then the last switch sets memory suspend. And then of course, if you want to reset the program, you can just press this button here, which will reset it. And then we can go back to max clock speed by turning off all these switches here. in which case the lights will appear to not be blinking because it's running so fast. Next, I'll demo the final program running on my DE2-115. I have it set to run at full clock speed. This program will take two signed 16-bit integers and give you the product. So let's start with an extreme number. Let's do negative 32,768 times 1. This gives you the same answer. If you can try 123 times minus 123, which gives you minus 15,129. We can try 45 times 100. This gives you 4,500. Here's the block diagram for the system. At the bottom, you have the sequencer, which generates control signals. Towards the middle, you have the register array, which takes 3 input registers and 3 output registers. PC is also register, but it's a bit separate because PC can be modified directly as well as modified automatically to get the next instruction. For a clocking scheme, the processor is driven by sysclock1, a 25 MHz clock generated by the memory controller. The clock cycle has 4 phases. Clock high, the FSM determines the next state and is ready to be loaded into the FSM state register on the next falling edge. Falling low, transitions the FSM to the next state. Clock low, all combinational logic propagates in cycles. Duration is adjustable via clock divide limit to accommodate propagation delay. And rising edge, registers are clocked, latching new values. After a reset, the first clock edge is a rising edge. Here's a diagram. If you look at where the falling edge happens, that's when the FSM advances to the next state. Signals propagate during the falling edge phase, and destructive actions take place during the rising edge. For sequencing, the FSM has 34 unique states. 28 states are for the memory read-write protocols, 2 states for reset and idle, and 4 states for increment PC, decode, instruction ALU op, and instruction immediate. Compute next state signals using combinatorial logic, and update the state on the falling edge of the clock. Here's the FSM state diagram. Most of the states here are for the memory handshake. Towards the upper middle, you can see the increment PC or decode and instruction ALU op and instruction immediate states, as well as the reset and idle states towards the very top. Special features for this project are a hardware multiplier and barrel shifter. The hardware multiplier is implemented by a tree of partial sums with binary multiplication. Once the partial sums are generated, they're added using 8, 4, 2, and 1 tree to generate the final instruction or final value. Barrel shifters are done by using by taking a subset of bits from the left or right and appending zeros or replicating the sign bits for arithmetic right shift. Because one of my special features was a hardware multiplier, I wrote a special benchmark to test the performance of software multiply versus hardware multiply. So let me kick it off here. So the difference was about 10.81 seconds versus 0.44 seconds for hardware multiply. So it's about a 24 to 25x speed up. Closing thoughts. It was very costly to make any modifications to the ISA since everything has to be updated. Initially, load byte was a macro and subtraction was native, but I found that dealing with 16-bit alignments would complicate both the hardware FSM and the ISM code. So I actually went back and revised my operation doc and turned load byte into a native instruction and subtraction into a macro. No cache means programs can quickly become memory bound. There's no instruction, no data cache for this project. Addition can be optimized by replacing the ripple carry adder with a carry look ahead adder. This would also optimize multiplication as well. Compared to high-level languages, fixing bugs in ASM is cumbersome. There's no type safety, easy to miss a push or pop, register number typos, and other minor issues which are not because of the lack of type safety. One thing that helped was I implemented an assertion library that helped catch multiple bugs. So I would highly recommend having some way to check if your assumptions are correct. Having only 16 native instructions forced heavy reliance on macro instructions to keep the assembly language from becoming unwieldy, which is why there's 16 native instructions and 30 macro instructions. I'd like to thank Professor Jamie, Mark, Stefan, and all of my classmates for this amazing course.